Well, good morning, everyone. It's good to be back. Uh, yeah, I was really sick there for a while, um, but feeling mostly better. My brain is still just a little bit foggy occasionally, so hopefully not too bad. And we'll go ahead and get started. I did some coding while I was sick, which is always funny because you look back on it and you're like, yeah, that's horrible code. I'm going to actually be looking back on it today. I just took one day when I was sick and really bored, and started working on some of the state for the PEG stuff. And actually at first I did it all with structs and ref structs and all this stuff, and it was interesting, but ended up being a pretty bad idea, I think. So I actually already changed most of that to classes. And we'll be taking a look at that today, and I'm going to try to figure out what I was thinking 2 weeks ago. So here we go. Let's see. Okay, so I didn't actually commit any of this. So here's all the things that changed, which is quite a bit, but it's mostly around this state here. So let's go ahead and take a look. Oh, yeah, and also, I did run into a rather annoying limitation. The source generators have to support, I think it's Net Standard 2.0. Yes, it's Net Standard 2.0. The source generators have to support this in order to be loaded into Visual Studio. The problem is I wanted to use some newer types, so trying to think of which one it was now. Got that brain fog thing going on. Yeah, so I want to say that it's let's see, that it's, what was it? Was it span? Yeah, it was span that I wanted to use. And I don't think that there's a package for span in that standard. Or there is. Is there? Boy, I can't remember anything right now. Anyway, well, let's look at the code anyway, since that is neither here nor there. So I started, thinking about what our state would look like. Our state is something that's going to have to be captured in the memoization cache. So what I wanted was something that's very fast to compare. So we could say, is this state equivalent to another state very quickly? And actually equivalent, not just reference equality. Because if state changes one way at one level and then changes back, I would want, I'm not sure if our current state can do that, but if it ever does, then I would want those to be considered equivalent. So what I ended up with is and I think that this is still a good idea, is to have this kind of hash value that's representing the state. And this is going to be a strong hash. It's going to be I think I used SHA1. So it's fast. It's not something you would want to use in like cryptography reasons because it's considered broken. But it's still considered good as far as not causing accidental collisions, which is what my concern is around. So SHA1 was the algorithm that I chose for that. And so what I ended up doing, because we've got these different kinds of states, so we've got the backref state, we've got the Boolean state, and then we've got what I'm calling the set state, which suddenly seems like it's kind of a bad name. Because set is usually used as a verb, and here I'm using it as a noun, like a set of things. So I might want to rethink that name. But anyway, I've got these different kinds of states, these three different types of state, and then all together that is like the state, right, of the parser. Well, that's the state variables of the parser. There's more to the parser state. The position is also part of the parser state. So anyway, so I've got like this almost like a tree of state. So I was thinking of doing it like a Merkle tree, where you hash each part of the tree only one part of that tree is going to ever change at a time. So you just keep one hash, and then you've got like this overall hash, and then that overall hash for the total state can be compared extremely quickly. And then I think I'm going to take that, our variable state hash along with the current parser position and call that the parser state. That's what I'm kind of thinking. I haven't actually done anything like this, so we'll see if it works out or not. Well, we've got this backref state over here. I'm just going to read through the code a little bit because, like I said, it's been a couple weeks even since I wrote this. So what I think what I ended up here, this was originally like a bunch of ref structs and stuff, and I reviewed it again a few days later, and I was like, wow, this is horrible. So I already changed that, and I'm gonna review it again now that my head's a little clearer, and take a look and see, if this still makes sense. So essentially, each of these states are gonna be following the same kind of pattern. It's a reference type, it's going to be immutable, and it's going to have a pre-calculated hash. Let's look at the hashes first, actually. I actually made a base type for that. Okay. So these all have a hash, and this was also originally a struct ref. But the idea here, ooh, wow, this is interesting. Not really sure if I want that. Maybe that's really ugly. So essentially, hash value is supposed to be immutable, and it is a reference type, and it's, what is it, 160 bits, is that right? Yeah, 160 bits, or 5 integers in this case. So 160 bits holding the SHA1 hash value. Now all of the equality here is done, it's value equality, and it's immutable. So it's logically kind of like a string type, similar design to that. The one thing that I'm seeing here that I'm not liking is this this span here. Oh yeah, I really don't like that. So what this does is it gives a read-write access to the underlying bytes. And that write part is the part I don't like, because this can be called really at any time after construction. I think I'm gonna have to change this. We use it when we generate the hash value, looks like. So let's see here. Okay, so this is right. Oh, okay, yeah. Because Net Standard 2.0, even though you can get the spans into it, right? Starting to remember this here a little bit. No, okay. Well, I think immutable actually pulls in memory, which then includes support for span. But all the span-based APIs are missing, right? So here's this like this wrapper around an SHA1 hash. With some convenience methods for hashing some things, including combining hashes, existing hashes. And right, like this kind of thing. Blah. I really don't like this, but I don't know of a way to avoid it in Net Standard, where if you've got like a span of bytes, you actually have to copy it into a byte array and then append it. Awkward. Annoying because it's inefficient. But in any but this would only happen in Visual Studio, which requires the .NET Standard 2.0 support. If you're consuming this, I'm expecting it will be being consumed in like a .NET 6 kind of project. that's kind of what my goal is for this. Is really this is only PEG support for modern code. Although technically it would, I suppose it may support Net Standard 2.0 in the end. We'll see. So let's see here. We've got, right, so then we can append spans and values into the SHA1, and then getting it out, this is where we actually have that that dot span that's being used, and we're also using it in the Net Standard code. So this is the only time that it's used. It's in construction, and what I'm thinking is it might be trying to remember my delegate allocation. Well, I think I'm gonna do that because I like the API better anyway. And even if it's a little bit of overhead, I'm gonna say that's good enough. So I'm gonna change this to use a constructor that takes an action, which takes, it can't take a span, can it? No, because it can't be a generic argument. Grr. Okay, so maybe this isn't going to work. I was thinking I could take like a constructor well, at the very least, can we hide it? I'm not sure if we can even hide it. I think we can hide it. Let me see. If we put this behind an interface, would that work? Looks like it would. Not giving us any problems there. So let's stick this in here. And then this is going to become an explicit implementation. Which has to be called such. Okay. So now, you know, it's still there, but it's not obviously on the, it's not obviously on the API. So at least it's not going to be easily misused. Awkward, yes, I really want to use this dangerous method thing. Yeah, better than having it public at least. Okay, so back to where we were. All right, so we've got this this hasher. Yeah, so we've got a hasher which can hash anything into SHA1. We've got this hash value representing an SHA1 hash. And then we have, let's see. No, oh yeah, back to the state. Let's look through the state here. So, again, the idea is reference type, immutable, with a pre-calculated hash. So in this case, we've got the backref state, and honestly, I don't remember what this is doing here. Let me pop open my docs. All right. Yeah, state. Here we go. So, looking at the docs for our state, we've got backref state, which is for backrefs. Here's the operations we can do. We can set a backref to some parsing result. Okay. I'm not sure what those results actually look like yet. Then we can match the literal string And that's a string match, which is interesting. I'm not sure if we want the result of this parse to be a literal string or if we want it to be the result of like the original evaluation. I'm not sure if we can do that. Might have to be the literal string. Anyway, and then we've got this this scope. Okay, scopes. We've got the scopes all separate right now. Okay, that would probably work. All right, and then we've got like a code equivalent of doing this. So let's see. So we've got, you know, some empty thing. Okay, so that's where this input range comes in. This is like my placeholder for, yes, this is my parse result. So let's take a look at this. Oh, right, it's just start and end, which is really the same as, it's not an index, it's range. Right, so this is essentially range. I don't remember why I wanted to do it, like have my own type. We'll keep it for now. All right, so we've got this empty backref state. What is scope? Oh, there we go. Okay, so this is in the base type. So we have, maybe I should read my own docs here. All right, so yeah, we want it immutable. We want it to have a pre-calculated hash. Makes sense. Okay, so also for our state types, if any no-op modification comes through, it actually always returns this. That's guaranteed. Oh, okay. So we do have one-way modification. So it's not possible to modify state and then back to a different state. Would we still need a pre-calculated hash if that were always true? That one I'm not sure about. I'm not sure if we actually need the hash then. Okay. And then we've got, okay, so this scope is actually a hash value, which is, let's see. Okay, so each time that this create method is called, it gives you back a new hash. And this is just kind of, so that our hash for one type of state is never going to be equal, if it's empty, is never going to be equal to the hash for another type of state, which is also empty. Those hashes are still going to be distinct. That's what that's doing there, is this scope. So let's go back to our backref state. All right, I'm starting to remember what I did here a couple of weeks ago. So we've got our backref state. So this is going to be, we're always going to be passing that scope in, and it's just going to be the same scope. This is scope because there's nothing else there. Okay, got it. And then what we're actually holding is a dictionary of integers to input ranges. That's interesting. What's the integer here? Oh, right. Okay. Because our names, so the thing I was thinking with this is when we parse a grammar, all the names are not going to be stored as strings in this state. They're actually going to be stored as integers. They're going to be reduced to identifiers, essentially like registers. If you're thinking in CPU terms. So so no matter what the user calls this, it's going to be like allocated into an array, and our internal state is just going to deal with the integers. So this int is actually the name. the unique identifier of the name. All right, so then we have a dictionary from the name to here's the result. That makes sense. All right. When we read it, we just see if it's in the dictionary. If it's there, we return it. If not, no. That's, yeah. So adding it, this is immutable, so it's returning a new instance, a new modified instance. And it's got this hasher in it, which is interesting. Look down at this create method. So when we create a new one, first it checks if it's empty. If it's empty, then we return that constant. We get that reference equality going. And then we append the scope, which we have to, and then for each backref that we've already learned, we have to include in the hash the name, or the key, and the result, the start and the end. This is assuming that they can change, which I think that they could. There's nothing that says you can't set it to one thing and then later set it to another thing. I'm not sure if we want to allow that, but fine for now. All right, and then we create the actual new backref state, and this creation requires a current give me the SHA1 algorithm, essentially the algorithm wrapper. So that's what this is. It's taking, and I'm passing these around because I don't want to be creating the actual SHA1 hasher over and over again. So they're just passed through here, which is fine. It's an ugly API, but it's not hurting anything. All right, so when we add a key and a value to this, yes, because the immutable collections also have this identity preserving property. So if set item doesn't actually change the collection, then it's also equivalent, and then I can also return this. So that makes sense. Here's our read and our write. Both of those make sense. Everything else here makes sense. Okay. So the backref state, I think, looks good. We did tweak the hash value a little bit. Let's take a look at the Boolean state. So Boolean, I was going to say it's either true or false, but actually it only holds true values. So we've got this immutable sorted set. Oh, it's sorted so that hashes of equivalent things are also equivalent. Okay, and this one's also sorted. Good. It's immutable sorted dictionary. All right. All right, so let's walk through this one then. We've got an empty, which looks right. Here's our read. Does it actually contain this name, right, which has been already converted to an integer? And then we add a new one. We've got our identity check. Yeah, this all looks correct. Very similar to the backref state one. And we've already looked at hash scope and the state base. Let's look at the set state next. This is the horrible thing. Got to change this one in. Okay, so this is a. Remind me what set state is here. To provide a set of strings. So our operations are we can add a new value to the set. The next operation is to match an expression in the input, determine if its string value is already in that set. So it has to match. Got it. Otherwise, the parsing result will fail. And we want it to fail there because then it'll backtrack and say, okay, this is not, an identifier. It must be something else. So that makes sense. And then we've got our scope. That's fine. Okay. And this scope is different than the scope type in, or scoped value in here, which might also be confusing. So what is a string memory set then? I don't know what this is. Let's see. Oh, okay. Interesting. Okay, right, because in this case we actually have our set state is actually going to be a collection of collections. So each of those, it makes sense to have their own hash value also. So that's why this is defining its own pre-calculated hash for each set of strings inside of the value. All right. Let's see. We've got our operations. So in this case, inside of this set, what we want to do is add if it doesn't already exist, and we want to check if it's there. Let's do that. So checking if it's there is very simple. Adding it. I don't know what I did here. What's equatable memory? Wow, this is getting a little complicated. All right, so let's take a look at this equatable memory. Oh, man, the code you write when your mind isn't quite right is always dangerous. So I want to go through this. What is equatable memory? Oh, okay, right. This makes sense. So the idea here is it's really just a read-only memory, which is something that already exists in the runtime, or in the system memory package, I think, in net standard. So we've got this read-only memory struct, which is really just a byte array. It's actually like a byte range in memory. But in this case, it is also equatable. So equatable memory is something that knows how to compare itself to other memory, and it just does that by comparing the bytes directly. So we've got this, so it overrides equals with a span equal, and then the hash code, same thing. Right. Okay. Yeah, so that's something in .NET 6. No, I think it's actually, this is actually in, this is also available in net standard. Fascinating. So where's this coming from in net standard? I just got to look this up because I don't remember this. It's got to be coming from a NuGet package, right? All right, Microsoft BCL hash code. Okay, so this hash code is a newer type that's also available in a package, apparently. That allows you to combine hash codes, essentially, and combine you can hash code. You can hash different things. It's not just other hash codes. Yeah, so it's for combining these other hash codes. It's also for just kind of like a general purpose hash there, which is how we're using it here. Now this is a very different kind of hash than the SHA-1 hash, the pre-calculated hash. That one has to be very, so the SHA-1 hash has to prevent accidental collisions. This kind of hash, this is a get hash code implementation, right? So it's a .NET runtime hash. Much more relaxed. Collisions are fine. But all it has to do is match the semantics of equals. Okay, so equatable memory is really just, I'm going to stick in a comment in here since I spent all that time figuring it out. A read-only memory that is equality comparable using the range of bytes as equivalence. Maybe my brain isn't quite working yet again. I'm going to keep it as that for now. But the idea is it's read-only memory is just a span of bytes, or not a span, but it's a range of bytes. And equatable memory is the same thing, except you can actually compare them to each other. All right, so we've got this equatable memory back to where we were here. Right, so seems a little more complicated. I'm going to start down here with the create method. All right, so we've got this, it's storing an immutable sorted set, which makes sense, except that it would also have to have less than, right? You would think. There's no restrictions on T here, but there is an I comparer. Yeah, this is not going to work. Okay, so this equatable memory also has to be like a comparable memory. It can't just be equatable, it also has to be comparable. And I'm not sure if memory span has any kind of... They only have sequence equal. Okay. So this is not going to work currently. It would work if this was an immutable hash set. But then the problem with that is our keys are no longer guaranteed to be in a specific order, which also means that that this hash can be different if it's... Our hash could be a different value for equivalent sets that were created using in different ways. So, yeah, we're going to have to either make equatable memory comparable, which should be doable, although I don't see any easy API to implement that with. Or the other option, which I'm kind of leaning towards, is jumping back into this hash state base. If this is true, this one-way modification, if this is true, then we don't need hashes at all. Is that true? Let me see this. So let's look through all of our state. You can set a backref. Can you set it to something else after it's been set? That's the question here. So with set state, you can't, right? You're adding this to a set. If it's already in there, this is just a no-op. You can't change it. You can never take one out. Set state does not require a hash. Boolean state can both be set and unset. Okay, so that again, and this one can be removed. Okay, all of the examples around Boolean state do not use this. We could remove it, which would then make it all of the examples that I can think of don't need this, I should say. Which would then make this allow reference equality instead of comparing by the hashes. This one is the big question. Does back reference state? You'd have to allow setting it to a different value inside of a scope at least. And that is a problem because it can go back to its original value. All right. So in general, this is not true. It's not possible to modify state using one API and then modify the result back to the original state. That is not true. Which also means that we can't use reference equality, we have to use the hash equality. I'm just going to say that. All right. Okay. So, unfortunately, that means for our set state, we really need a comparable memory, right? Because this has to be sorted. This immutable set here has to be sorted in order to have our keys always come out in the same order, which is necessary in order to always have the same hash for equivalent sets. Annoying. All right. So let's take a look at this equatable memory then and see if we can change this to a comparable memory. And I'm not sure how easy that would be. Boy, that's a good question. So this compared to has to do essentially like a byte range compared to on the underlying memory. I'm not sure if there's any way that we can do that. Easily. Not seeing if anything is possible. It could be under like memory marsh. It wouldn't be under memory marshal, I don't think. Sometimes with the spans and the memory stuff, there's things are in places where you may not think they are. Okay, so let's see what Stack Overflow says. All right. I want to take let's say, right, so this is a read-only memory. Well, let's just say memory compared to. Yeah, memory extensions dot compared to. So, all right. Why this isn't showing up here? That's exactly what I want. So why is this not being found by IntelliSense? So it takes a span, right? Memory.span.compared to should be right there. It's in memory extensions. Weird. I don't know if something's messed up with my IntelliSense or what here, but yeah. Let's see. It's there. Interesting. Okay. For some reason, Visual Studio doesn't want to see it. Oh, it's read-only spans with char. That's not going to help. That's a string comparison, which is fine, but it's not what we're looking for. we want to do is a binary comparison over bytes. Although, this is storing strings. Right? This equatable memory is actually, yeah, an equatable memory of char. Yeah, so I can just say that this is an equatable memory string. And we're going to get rid of this this type here. It's comparable, and this is actually going to be a comparable. This is such a horrible name. It's going to be equatable of itself and comparable of itself. And what we're doing here is we're removing that generic parameter because I tried to make something that was too reusable. And I'm comparing these as ordinals, which I'm just going to say that's good enough. All right, so this will take just wraps that read-only memory, and then we've got, when we compare them, that's why I wasn't showing up in IntelliSense, because I had the wrong type. And this is going to be string comparison dot ordinal. Okay, so now we've got a compare to that should work, and I'm going to fix the rest of these methods. Equals is still going to be, well, we could do sequence equal. I wonder if there's an equal for strings. There is. Let's say that's probably faster. Let's see. And then our actual get hash code is still going to be the same thing. It's just, I'm just going to grab it as bytes. Let's check the net standard code. So the net standard code adds it character by character, which is awkward, but it works. I'm not sure if there's any other methods that would be better on that. No, I don't see any. Okay. All right. So again, in that standard, you have spans and hash code, but they can't work together because the APIs aren't there. All right. So let's see. So now we have this comparable memory string, which is just a string range in memory that can be compared to another string range in memory using value comparison, essentially, ordinal or byte-wise comparison. So now let's come on down here. We're using this comparable memory string now instead as our string value. And this should just pretty much substitute all the way across here. All right. I can feel my mind starting to catch up and understand this now. All right, so now we've got yeah, so we still need the hashes because we can change state and then, like within another scope, change it back to what it was before. And those hashes do have to match, or do they have to match? We might still be able to get away without matching those. But anyway, that would be an optimization for later. For now we have a comparable memory string which can actually be compared And this will actually work with an immutable sorted set. Okay, so we've got this create method that builds out this set. That all looks fine. There's no keys in this case, it's just a bunch of memories. Yeah. All right, and then we have, I've got this unit here, which is just creating a set from a single value. And then we have the ability to check whether it's in there, we already looked at that, and then to add a new one. Again, that reference equality is good, and then we create a new one, all right, which is not going to be empty. In fact, there's never going to be an empty set in this case. All the other ones that we looked at had like this special empty value. This one does not, because you can never have an empty set. It would instead be removed from the state completely. Okay, so let's go back to our set state now and make sure that this is all looking correct. So now we've got an immutable sorted dictionary. This is going to be the name. The name, and each name maps to a set of strings in memory. Okay, so this one does have an empty, which all looks perfectly normal here. Skip on down to our create. That all looks correct. Notice here we're actually hashing the hash value at this point because each set value has its own hash, and then we combine those hashes into this state. That makes sense. All right. And then, yes, so I made a note here. Does this exist? We have to decide, is this case sensitive? And right now I just said everything's ordinal. So, all right, so then the question of, does this name contain a value, or does a set represented by this name contain this value? So first we try to get the sets. If it's not in there, then it's empty, so we return false. And then we return whether the set contains this is it comparable memory string? Yeah. All right. So we just wrap it in this thing that says you can be compared. All right. And then that actually compares it by memory, by the underlying character bytes. And then we add one. We've got our, so we're adding to this name the this new value. So first, if there's no set, if the set is empty, you know, if that name doesn't have anything in it, then this would return, contains key would return false, and then we create a new one with a new, right, so all of the existing values plus this new name with a single value, a single set containing a single value. That's what I'm trying to say. And then we can pull into this this set and add the new value to it. If it's equivalent, then nothing changed. Got that identity equivalent still, and then we return the okay, got it. Yeah, because the new set then has to be saved into the immutable dictionary. Yeah. So that all makes sense. I think that all looks good for all of our state. I don't know what variable state is. What is this? Okay, right. So these are, we've got the three different kinds of state where we can store variables. Now we've got backref, Boolean, and set. Still hate that name. And then these three are combined into a variable state, which also has its own, have got an empty type. And then it looks like I just, looks like I've got the query and the updates for each of these different ones just hanging out for this variable state, which is fine. And here's where that Merkle tree is coming in, where you've got, it was also present in the set state because it was combining the hashes of each of those sets. And in this case, we've got three different kinds of state that we're combining into a single one. And we've got, in this case, the hash value for the variable state is just going to be the hash of the three hashes of its substates. That makes sense. This is also immutable. Oh yeah, this is actually a hash state base. Yeah. Okay. So let's just walk through these real quickly. I don't expect any problems. Essentially, we're saying try to get a back reference value, add a new back reference value. Right, because we've got that identity equivalence coming back. This is odd. We don't need to do that. This one can be a reference equality, and it would be slightly more efficient. Here. All right. And coming on down. So then we check to see if a value is in a set. And we can also add a value to a set. Once again, this dot equals is not necessary because this one actually does. Oh, I see. Okay, so dot equals, it does do the reference check first and then does the hash equals. It's fine, but it's really can be simplified down to just a reference equality there. And then same thing here. Adding a Boolean value, that looks good otherwise. Yeah, okay, so this is all of our variable state combined into a single type. So the state stuff looks good, the hashing we already looked at, and then I've just got these temporary things here for, here's our input range, which is gonna be, I'm using that as our result temporarily right now. This I didn't do anything, let's get rid of that. I don't know if I need this either. I don't have any records yet, do I? Well, I'll keep it for now. All right, let's just delete some of these other things that I didn't even look at. Okay. I think that's, okay, so today has been mostly like, let's look at what I wrote when I was sick and see how bad it is. And it wasn't too bad. It's fine. Okay. So yeah, let's build this thing up here. We've got some warnings. What's going on here? Oh, it's all, I've got this benchmarks project too that I added just to test out some things. This is using benchmark.net, which if you're doing benchmarks, you really should be using benchmark.net. It handles a bunch of extremely common mistakes when you're benchmarking code. So I've got some warnings in this code because some of this stuff I can't even compile anymore. So just ignore that. But yeah, benchmark.net is great for determining which things are faster. If you've got a couple of possible options. Right, so I think the last one that I checked here was actually in this hashing. So my question was, yeah, here we go. is sequence equal, which we have available, going to be faster, or is comparing every single one of these integer values individually going to be faster, and actually comparing all the integer values individually was faster. So anyway, so that's the kind of thing that you can use benchmark.net for. What I really wish they had in benchmark.net was a way to have like a baseline. Well, I mean, they have the ability to have a baseline, but I'm thinking like over time, where you've got like a baseline that's saved somewhere, and then some kind of like GitHub Actions output or something, or what are they called? Artifacts. Some kind of build artifact that you can save your baseline, and then the next build, compares against what's currently the baseline, or a PR build compares against what's the baseline in the master or root core branch or whatever. So that kind of thing currently isn't really supported well by benchmark.net. But what it can do is you can implement it twice, both ways in the same code, and then compare. You just don't have that nice history, that nice diff view. Like if you use code coverage, those kind of things, they all have good support for that these days, where your PR branches say this will increase or decrease code coverage or whatever. And I would really like to see the same thing for benchmark.net. But anyway, it's not currently there, but hopefully someday. So anyway, it's getting near the top of the hour, so didn't get to do a whole lot today, but yeah, looked through some of the code for the state, and this is all kind of speculative code anyway. It might completely change by the time this project's done, but it's something worth having for now anyway. One of the things that I was thinking of earlier this week was what I'd like to do with this project is do a peg parser generator, right? So you can parse things. What I'd also like to do is have a Visual Studio plugin and a VS Code plugin, so that in your grammar peg file, so this isn't really a grammar peg file yet, but in your grammar peg files you can have, I don't know if you can do, I want like code coloring, I don't know what it's called. Syntax highlighting, that's it, syntax highlighting, names right now, my brain's so foggy. Syntax highlighting and things like completion, IntelliSense would be nice, and like go to definition. So like if you're looking at in your grammar file and you're like, well, what is this? Maybe we could do like maybe even like a pop-up showing that definition, or at least an F12 to jump to it. That kind of thing would be really nice for peg grammars. So I want to do a plugin that does that, and there's a new way of doing that I just learned about recently during the reading of the last couple of weeks, and it's called a language server. So the idea is you're actually like running an HTTP server, and I think it uses JSON RPC. So you're actually like running a local server, and then your VS Code plugins and your Emacs plugins and your Visual Studio plugins all just talk to your local server, and to provide that kind of rich editor help. So that way you don't really only have to write it once, ideally, right? I think it's still kind of a new technology. How well it actually works in practice is not determined. But anyway, yeah, I wanted to include that in this project. So I want to do a full language server eventually, not just a peg parser. And then I was thinking, would it be possible, and this is a real stretch goal here, would it be possible to have not just a peg parser be generated, but can we flip a switch on our code generator and have it actually generate a language server for that PEG grammar, including things like, well, I don't know. We'll see. We'll see if that's even, or at least like the shell of one, right? So that you can define a language using PEG and then have a really head start, not just on parsing that language, but actually providing a language service for Visual Studio or Visual Studio Code or whatever. That's a huge, way down the line, pie in the sky kind of stretch goal for this project, but it's curious to think about. We will see. So thank you for tuning in this morning. It's good to be back. Maybe not quite 100% yet, but it's good to be back right now. And thank you all for coming. We will see you next time.